Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. This is episode 10. I'm actually surprised we've done so little of these, but it actually makes sense because we worked on this project a bit at the beginning of last year, and basically put it away for a little over a year, and now about a year and a half actually almost. Yeah, first try exactly, totally on time. We're doing great. No internet issues at all. I'm so bad at this. Anyway, um, so I've got a lot to talk about. I need to calm down for a second because my internet was being really stupid. But anyway, for those of you guys that don't know, xenowing is my kind of first attempt at making a whole computer on an FPGA. And more so than computer, it's kind of an homage to mid 90s game consoles, especially really ones with ridiculous names. Just because I want to make something at kind of that level. I want to build that system from the ground up. I want to understand how the CPU works. I want to understand how memory works. I want to understand how memory mapping works. I want to understand how GPU, all that kind of stuff can fit together. And what it's like to design a very basic version of all those different kinds of things and actually make them work together. So I started this project it's spring of last year, maybe winter. I think it was in February actually, and worked on it for maybe a month or so, and then kind of fell off, and we could talk a little bit about why. But I now work at a hardware company, and so I'm surrounded by a lot of this stuff a lot more now. And I just find myself being really interested and asking myself a lot of questions, which in my head are answered by doing things. So I want to work on this project again, and I'm really excited about it. So yeah. Also, we've been making some pretty good progress. We as in me, but Anyway, so I prepared some slides just to kind of keep myself on track because there's so much that I did, especially in the last like 2 weeks. I think it was about 2 weeks ago where I finally sat down again, and I was just like, you know what? I want to work on this again. I want to spend my next streams for the next little while to make as much progress as we can. I think we can actually make quite a bit. And then I just went nuts the last couple weeks on it, and I've been having so much fun. So there's kind of a lot that I need to go over before we dive back in. Unfortunately, I wasn't able to do any of it on the stream. I wanted to stream last week, but it just didn't work out. I've got a lot going on right now in my personal life, and that's eating up a lot of time, but that's good as well. So don't worry about it, but I'm going to try to keep streaming regularly on Thursdays. In fact, today's probably going to be a bit of a longer stream, which I'm happy about, longer on the range of like a couple hours. So not super long like I've done a couple times in the past, but I don't think we'll need to anyway. So what I did is I actually gave like a little presentation when I kicked off this project, where I kind of did some slides as well. And I had sort of these same disclaimers, where the first one, I'm not an expert in this. Like, I'm totally new to FPGAs. I had done a few projects that are very small on the same FPGA that we're using for all these projects. I haven't used other boards. I haven't used other pieces of software. I don't really know this domain, but I'm trying to learn. I'm very interested in digital design. I'm very interested in learning how to make stuff like this. So that's kind of the purpose here is learning how to build all this, and also just having a lot of fun building whatever tooling we need, kind of learning these different flows. How can we make some parts more fun to do? And I don't know, just try to enjoy ourselves while making something that hopefully is kind of cool. And a big part of that also is like scoping down a lot of stuff, which we'll also talk about just because this is a free time project. But yeah. Anyway, learning as I go, and I'm here to share. I won't do everything on stream, obviously, like I haven't done the last couple weeks especially, but Also, everything that I'm talking about will change. I'm going to go over some architectural details that cover what the project is right now, but this might change tomorrow. I don't think any of the stuff I present today will change tomorrow, but it might, and that's fine. This is a very organic project, and I think that's totally cool. So rough agenda for it today. I want to again sort of recap some of the goals that I set for the project last year, and a couple of those have changed a little in my head for various reasons. I also want to go over what we did last year, how far we got, and then how far I've gotten coming into this year, and then sort of ask ourselves what we're doing next, which we will ideally start today. Yeah, I know this is way too professional for me, but I just have to get some of this out of my head in a clear manner before it just all gets lost, because I'm just so excited about all the progress I made the last couple of weeks. Anyway, again, the main goals were to design like a stripped down 90s era console and FPGA. So I want essentially the entire system to be on one chip. So we can design all those parts and see how they fit together. I'm trying to do, it's not really listed here, but I'm trying to design everything from the ground up. So there's not going to be a single piece of hardware that we don't write, except I'm using an off-the-shelf DDR controller, which definitely saves us a lot of time. But other than that, all of the hardware is described by us. I think that's okay. I also want to explore existing FPGA tools. Like, what is it like to design something like this? It's like to design anything for an FPGA. And I also, especially, it says here, like simulation and compilation-based workflows. Like, can we actually do useful stuff with those? And the answer to that, I'll give a little bit of spoilers. Of course, yes. It's, if we keep everything in one clock domain, then we don't really have that many issues. And this kind of workflow based around Verilator and Rust, which is what I put together last year, I'm actually quite happy with. I want to cover some basic CPU and GPU design. That's still the most important thing. And then maybe some APU design if we ever run on the chip. And then I also thought about doing some case design and controller design just to kind of like make this a real physical thing. But of course, I've changed a couple of these goals in my head in not working in the last year. So definitely I want to do some kind of audio unit. In fact, we'll probably do a couple different ones. I don't really care about case design or interfacing with a controller right now. We may never do that, just because it doesn't really make that much sense. It's a lot of like physical design work that it's not really going to be my wheelhouse. So maybe we still do this stuff. Again, any of this could change, but this is kind of just to give you guys an idea of what I want to focus on. So the rest of this is still absolutely accurate. And yeah, work instruction says networking. No, I don't think I'm going to do any networking. I might do, there's some of the stuff I might do. Well, we'll talk about it later, but yeah, I don't think I would say networking is definitely not on this list. But there may be a way that we can do that kind of aligns with some other goals. We'll see. But anyway, so basically, how far did I get last year when I worked on this? If you guys haven't seen the streams or anything. So we got the basic project and repo set up. So I could just pull up the folder, I guess, but it doesn't really matter. Whoops. We have some RTL, which is the actual code for the hardware. That's in System Verilog, and we got a basic project set up around that. So I have essentially, there's a Quartus project, and Quartus is the Intel tools. It used to be called Altera. They were bought out. I think that was last year, or maybe the year before. Anyway, I have an Altera FPGA now, again, Intel FPGA. So I'm using those tools to actually run it on the thing, but at the same time, all of our hardware code and everything should be able to be iterated on without the actual FPGA itself. And the big reason for that is the design, even with as small as it is right now, with just a few basic components and a DDR controller, it takes like 5 minutes or something, anywhere from basically 3 to 10 minutes, depending on if I'm on my desktop or my laptop, to rebuild all the hardware and get it onto the FPGA. And that's a long time when we're just iterating on something, especially if we're iterating on something that's very simple and we'd like to just kind of work on it quickly. So that really sucks. So we just want to have this kind of simulator-based workflow as well. And so I set all that up as well. I'm using a tool called Verilator, which will compile a Verilog to a C++ simulator. And then with that C++ program that it generates, I load in a Rust, I make a Rust library that I load in, and the Rust actually drives all of the simulation then against the C++ simulator. And with that, we're able to do like this DDR3 simulator in Rust and have it working with our compiled hardware code and iterate on that very quickly. That seems to work really well. I'm quite pleased with that. So, and of course, all this works because we have what's called a single clock domain. So we're not doing anything crazy with timing. We will talk about timing later because I had a lot of fun with that this last week. But yeah, essentially we can kind of scope down some scope of our design and then keep that as a good workflow. And I think that that's a really smart thing to do. It says, so all this is open source, by the way. It's on my GitHub under the repo xenowing. And I haven't done a lot of like documentation on that just because a lot of this wasn't solidified and I was still working on it. It might actually make sense for me to start doing that now. And also there's no license because I was having a really hard time evaluating and finding open hardware licenses. Because it's a little bit different than just shipping the software and putting that under a software license. Although a lot of the generated components that we use for the DDR3 controller actually do that. They just have a BSD3 license. So maybe we just adopt that after all. I'm not really sure. Again, if any of you guys have any experience with that, I would love to hear about that. So, because I would like to license this like that and like make that kind of proper, but yeah, I just don't know. I just don't know enough about hardware licenses to be able to pick one. So that's the only reason I haven't actually licensed it. Maybe it ends up going in public domain, but again, what are the consequences of that? So I just would like to know more before I decide on one. Anyway, we got the DDR3 controller working. I think I spent like 2 weeks just on the FPGA with those like 5-minute recompile times, just trying to get it working. And then once I finally got it working and got like a reliable test, then we were able to model it in Rust. And then the iteration is really quick because then we know how that interface works, at least the subset of it that we're going to use for this system, which is pretty basic. The controller can actually do a lot more. It can do like burst reads and writes where you get a lot more bandwidth. And maybe we want to open that up in the future when we're starting to do like the GPU and stuff, where we know the structure of the memory reads and writes up front. We can kind of design our pipeline around that and get better throughput. But for now, we're just going to keep it as simple as possible. We can do single byte reads or writes, or actually single word reads or writes at a time, which even from the CPU perspective, we've already limited to 32-bit words, but the GPU could probably access 64-bit words kind of as is, and we haven't really changed too much. So I think that's really good. I got the first working risc-v implementation, which I was really excited about. That's the first time I've ever actually designed a CPU with digital logic rather than just like an emulator or something. So I was really stoked about that. Also, we got the main system architecture established, memory map and interconnects, so all the stuff that connects the CPU to the memory and everything else that it's connected to. And we got an LED interface because there's a few LEDs on my board. In particular, there's 3 of them. And that it works that we can address those via 3 bits of a register in our system. And then also I can send over UART, which I can set up on my PC just to listen to like a COM port, because my FPGA has a little FTDI chip that takes in UART and then sends it over a virtual COM port to my PC. And that goes the other way as well. So what I've been using that for is I set up a little ROM reloader, because again, with all of this set up, it works really well to use like the simulator kind of workflow, but this system actually runs at 150 megahertz, and that's just too fast to be able to simulate in real time on my PC. One of the things I thought about doing is actually just clocking everything down, and maybe even dropping the DDR memory and just kind of making this a really simple system that I can essentially run real time. So it's kind of like working on an emulator, but we're doing it in hardware descriptor language instead of software. And I think that could be really fun. I might still do that. But at the same time, in my head, it's still, I have this glorified idea of making a really crappy rasterizer and stuff that I really want to run at a higher clock rate. So I still would like to focus on that goal, at least for a little while longer. But again, a really important part of that is eventually when you get to doing that rasterizer, I want to prototype everything in software. And the ability to reload the ROM without recompiling all the hardware means that we're iterating on the order of a few seconds rather than a few minutes. And that should be, that's going to make a world of difference when we're actually making this stuff. So I want to kind of prototype all that stuff in software, and when I kind of figure out a nice way that I think it could work, then I want to start moving parts of that into the hardware kind of progressively. And I think a lot of that can again be done in simulation, and then I think that'll be a really good workflow. So the problem with that though is that when I initially implemented that, it was really unstable and it was really hard to debug. And I think that I had gotten that far, and I started to get really demotivated about it because I had put in so much effort getting the memory to work, and then I kind of got the CPU to work. Everything looked like it was good. And then I went to do this ROM reload, which should have really helped. And it shouldn't have been that terribly difficult, but it was really unstable. And I got really frustrated with that. And then revision was coming up, so I kind of focused on that. And then a lot of other things happened. And then the project kind of died for a while. But this was actually a lot of progress it's the first CPU I've ever designed. Everything before that was just on the same board. I designed a couple of simple state machines. I did actually get video output out of this board before. We'll talk about that a little bit later, but not much beyond that. But all that stuff was really difficult for me because it was kind of just bootstrapping everything, and I was really blind. Whereas this was a lot more focused on, okay, we know this is going to be difficult. We know things are going to be hard. So what can we do to make life easier for ourselves? So for example, can we rely on that simulation-based stuff? And yes, that's awesome. Can we get to a CPU, and can we use the UART for debugging for the CPU? So now we have put S, so we can write strings out to the UART, and that really helps because we can read those on the PC. And in fact, I'll talk a little bit how I was implementing this UART thing. Again, kind of with that philosophy, or with that, I don't know if it's a philosophy or just kind of a mindset of just like, we know things are going wrong, so how can we kind of design all these little tests so that they're not super frustrating when things do go wrong. So yeah, that's why I said we're doing great, because I'm actually super proud of this progress, even though the project kind of died for a while. But it never really died. It was just it was in the back of my head a lot, and I was still kind of frustrated about it. But we're hitting it again, and things are going swimmingly, for a word. Anyway, so going into 2019, we've picked up a bit of the project again. I've actually re-implemented the entire CPU, and I think this was the biggest thing that was in my head since last time. I had implemented the CPU as this really big kind of single state machine with all these signals and registers and stuff, and it looked a lot like what you would write as a CPU for an emulator. A big kind of switch case with all different states and everything, and that was a way that was easy for me to think about, and I was able to get it to work without too many issues. But it looked really bad in like the RTL viewer and stuff, so the design clearly wasn't as simple as it could be. Especially if you read the risc-v documentation, they make a lot of decisions in the ISA that are supposed to make it like easier to decode, and to me that should translate to relatively straightforward looking hardware. And it didn't when I had implemented it first, so I want to do that again. I was also thinking about like memory latency and some other things, and I thought that, yeah, we're running at 150 megahertz, but all my instructions are going to be like 5-6 cycles long, so we're not really utilizing that very well. So eventually I would like to look at pipelining. I've actually kind of taken a step back from that. I might not actually do that during this project, but maybe we will. The point is, though, that I want to have that option. So I want to design the CPU to where it probably makes more sense that if we want to look into pipelining, we don't have to re-architect everything and build it from scratch. So that was kind of important. At the same time, I also, Verilog is not that bad of a language, especially not system Verilog, but to me, it was always kind of hard to reconcile in my head, because I was trying to build these mental models of how the hardware works. Again, I'm really interested in the digital design part. And yet when I was writing Verilog, I just felt it was very indirect and that I was writing a lot. And I also chose a fairly verbose style to write the Verilog in, which is like this 2-process style. And I also think that wasn't conducive to kind of breaking the hardware down into multiple units. And I think if you write much smaller units in sort of this 2-process style, you end up with kind of the right sort of mental model, but then you're still writing more than you have to. And so then I kind of want a language that kind of supports that and also catches more errors for me. If I'm doing assignments where the bit widths don't line up, I want that to error all the time and be very loud about it, rather than just like silently ignoring a lot of that stuff and then me having to debug that kind of thing. So I want kind of a simpler model, and it turns out that I was able to do that where I kind of just designed my own Python HDL. It's kind of a crazy idea, and it's not that big, so I don't really feel like it's a bad idea, but we'll talk more about that later. Anyway, I'm really excited about it, and now I have a CPU.py, which has most of the CPU in it. Some of it's still system Verilog, but I'm really stoked about that, and we'll talk about that. I haven't looked at Spinal HDL. I looked a little bit at MyHDL and Megan and NMegan, but I haven't looked at them in that much detail. I actually wrote this first, and then someone told me about those, and I just started looking into those, and I think mine's closest to Megan or NMegan. I don't remember which is which, but it ends up being a pretty close mental model to that, which I think is maybe validating, and that maybe I have a mental model that's good, or that at least other people seem to agree is workable. But in any case, for me, it's just been helpful to kind of write in a way that's closer to the way I'm thinking about things, and still get the same kind of hardware out. So I'm pretty happy with that right now, but we'll see. And then I also fixed the ROM reload and made that really robust. And again, I want to talk about how I did that in a minute, but I want to go over these in more detail because, again, there's a lot of things that went through my head. I'm actually very tired because I've just been, I don't know, I have this habit of when something like this just clicks, then like I have to act on it. I have to build things that just kind of verify the model in my head, and I find it extremely exciting and extremely fun, but I kind of run myself into the ground sometimes, so definitely gonna need to rest up this weekend, but I want to talk a lot about this. So again, I mentioned that the other one was kind of a spaghetti mess, very emulator code-like. It was easy for me to write really quickly, but then whenever I was looking at it after, it was kind of hard to reason about, and it was definitely more complicated than it had to be. If you guys saw the streams where I was like trying to get it to infer block RAMs and things for the register file, you can see that even after I did a lot of that work, it was still a really complicated piece of hardware when we looked at the RTL viewer. And I think that's a sign that the design is a lot more complex than it needed to be. And again, I mentioned that we might want pipelining. I might also want to put SIMD in this, because if we're going to have a rasterizer, we need to transform some vertices that we feed into that. And ultimately, you shouldn't necessarily be doing that with just scalar fixed point arithmetic on the CPU. But that's probably the first thing we're going to do, so that might be fun later. But anyway, I also just kind of wanted to, like I said, I work at a hardware company now, and we make silicon at the company I work at. I don't directly, I work in software there, but I'm exposed to a lot of this, and so I talk to a lot of those guys and just try to understand how things work at a very low level. Obviously, you guys know that I'm really interested in that stuff. That's why I was making emulators for a long time, and still working on Rust Boy. So I just really want to understand this, and I wanted to. I was also reading a lot about existing architectures, and just like, okay, I can kind of steal some ideas from there, or try to implement this with a lot of those existing ideas. So just kind of wanted to take another stab at it. I also thought that would be a good way to kind of get into this, rather than trying to wrap my head around the old one and kind of try and sort of untangle it. I decided I'd make it from scratch, and obviously that was a lot of work, but it was a lot of really fun work. And I completed that in like a week and a half in this new language while making the language, so it's kind of cool. So some key points about the new design. I wanted to think more on hardware, and instead of having this big stupid state machine, I wanted to have the different stages that an instruction goes through as individual units of hardware. And this comes from like the classic RISC design, where we have like an instruction fetch, decode, execute, mem, write back. And I wanted to just like, okay, let's build our new CPU with those same stages. And initially, what I wanted to do is, or what I ended up doing is, I of course built those stages so that they could be ran independently. They could be so we could actually get a pipeline implementation. But the first, when you have pipelining in a processor, you have a lot of data dependencies that you have to work out with, or you have to work with. So you might have stalls or hazards or whatever in the pipeline. Might have to invalidate parts of that, all that kind of stuff. And I decided, let's forget about that for now, and we'll just have some control that just enables each state one at a time as the data is flowing through for a single instruction. We'll just go in that kind of loop. So we still don't get like the performance benefits of doing this new approach, but we get a simpler architecture, and we're one step closer to pipelining without having to commit to the entire pipeline implementation with all of that extra control logic. And that might not actually be that difficult now that I'm seeing what this looks like here, but we can still put it off, which is something I want to do, because ultimately I'm more excited about getting to the GPU than I am about CPU pipelining. So that's really nice. But also it just makes the design like super predictable. Like each stage is just going to execute in its own sort of phase. Each stage only cares about its inputs and its outputs, and we only know one's executing at a time. So it's a lot easier to reason about what the CPU is doing at any given moment. And kind of look at each piece in isolation, I think. Also, again, minimizing as much as possible. Like I said, the RTL viewer from Quartus was just exploding with the design we had previously. And I wanted to just get a better mental model and sort of think more about this. One of the features I removed that was in the other implementation is unaligned loads and stores. So if you like write a word to an address with the lowest couple bits set, then this should actually do an exception or a trap. Right now I just silently let whatever happens happen, because that simplifies the design, and then we can just make sure the compiler is not generating any code like that, and it's actually going to be fine. We can be a little careful about that in the software too, and maybe I do actually implement traps for that case, or at least just like a fatal exception. That might help with error handling later, or catching errors if we might make mistakes later. But so far, I don't think that's going to be a problem. Maybe I'm wrong, so this may change. This also may change in case we want to use the UART receiver for anything that the CPU can see. I might want interrupts for incoming data. Again, we'll see. But right now, not doing that. And then I have this point that says separate control and data paths. So this is something that is obvious to hardware people, but is kind of still a new concept to me. And that's the idea of like, if you're gonna put a value on a bus, like if you want to do a write on a bus, you're gonna put your bus has a bunch of data lines and some control lines. So a data line would be like, here's my word that I'm writing, and then the control lines is like enable write. And the thing is that for a lot of this logic, the enable write is actually kind of the important part that you want to like gate a lot of your logic on. It doesn't really matter if you put a byte on the bus for the cases that you're not actually doing a write. It doesn't really matter if data ends up on that bus without the data write signal valid, as long as you're not doing writes. My point kind of being that like if it simplifies the design to put stuff on the bus anyway, whether or not we're going to actually use it to do a write, then let's only gate that logic on the write line and have all the logic there and just let the data path do what it normally does. And so I'm really pleased with that sort of philosophy, actually, because again, it makes things really simple because we just don't have to care about a lot of those cases. And it also makes our hardware a lot smaller because suddenly a lot of the data paths, again, are a lot simpler, and all the logic is just on the control paths. This may not be that obvious when we start looking at how I actually did this. And I won't go into too much detail about the code probably today. But it's just, I think that's been a key thing that's been in my head this time. And I'm really happy about thinking in that way now. That's something that I will definitely continue doing while designing this kind of logic. So I want to talk about the pipeline stages that I actually ended up with. And this is sort of the highest level overview I could give of the processor. So if you guys are familiar with classic RISC, you'll see instruction fetch, decode, execute, mem, and write back. Those are all the same. I ended up with another stage in here, which is called register wait. And we'll get to that in a minute. But anyway, these are the different stages. And then there's this control logic that kind of handles everything in between, which right now it just has a state machine where it goes through all these different states. And normally it just has an enable line where it enables one in turn, and then it'll enable the next one and the next one and the next one as data flows through. The only real exception to that is that some of these stages, for example, instruction fetch can't actually issue the read for the instruction if the bus isn't ready. So there's some feedback going into the control logic that says, hey, you need to wait. You can't move on yet. So what happens is it enables this, and then this will stay enabled in this state until there's a cycle where this was enabled and then this said it was ready. And then when that happens, it goes to the next stage and basically does that the entire way through. Not all of the stages actually have that feedback. The execute stage, for example, doesn't, and the register wait stage doesn't. But instruction fetch, decode, mem, and write back all do have that logic to essentially stall the progress. And the nice part is with this control logic, it's just that state machine and then whether or not it should stall per state. And that's like all of it. So that's really nice. And then instruction fetch, all it does is take the PC and issue a memory write if it can, and stall if it can't. Decode just sits there and stalls if it's stalls while it's waiting for the data to come back from the fetch. That's all it does. And then it also outputs values into, or addresses into the register file. Register wait ends up reading the actual registers from the register file. Execute ends up doing all the work, and then memory either executes a mem read or write if that instruction needed to do that. And then write back will either wait if we issue to read and we need to wait for it to come back, or it won't wait, and then it'll just write everything back to the CPU state. So fairly straightforward. And yeah, but again, why do I have this register wait state? Why do I have this when classic RISC didn't? That's something I definitely want to talk about here. So originally, like I said, I had a classic RISC pipeline. In fact, actually what I did is instead of, this register wait would have been removed, and you'd have instruction fetch, decode, execute, mem, write back. That's the classic RISC pipeline. But actually, I also because there's no real data dependency between these that needs a cycle latency, I actually had execute and the memory states in one state. So I had a 4-stage pipeline, and that worked really fine in simulation and everything. Like I implemented the logic, it looked awesome in the very later sim, and I was really happy with the implementation. I thought it was clever that I could fold those states. In fact, I even started considering folding the write back and instruction fetch stages because that also works out with the data dependencies, and like 6502 and stuff does that. But what happened is I put this on the FPGA and it didn't work. And I wasn't really sure why, because like the simulator setup's the same. We only have one clock domain. There shouldn't be really anything spooky going on. I tried to debug this with a tool called Signal Tap, which it allows you to inject a logic analyzer in with your design when you put it on the FPGA, and that's really nice because then you can sort of tap onto a few signals and have it trigger on some condition, and then you run it on the FPGA. It will record a bunch of stuff using the onboard RAM, stream all that out to the tool, and then you can actually look at the waveform view for that stuff. And this is extremely useful if you don't really know what's going on with the hardware, except in this case, it actually wasn't useful at all because I could rarely get it to trigger. And even when it did, I would see weird stuff. Like I'd see it would try to issue a write to the UART, and then the write enable would be there a cycle before the data, which didn't make any sense. Those should be ready at the same cycle. And I really didn't understand. So I got really stuck with this, and I got really frustrated. But luckily for me, I mentioned I work at a hardware company now, and so we have FPGA engineers. So I just went to work, and I was like, hey, I have an issue here, and I don't really understand. So I asked one of my colleagues, and he said the biggest thing he said is that you need to make sure your timing is specified correctly. Now this I didn't actually know was something you had to do. I thought, well, the FPGA knows what my clock source is. Somewhere I can figure the clock. It probably knows that too, so it could kind of figure out all the timing and everything. But actually, that's not the case. You do actually need to tell it what the name of the signal that represents your clock is, and what the rate it's supposed to be at. And yeah, if you look at like any beginner FPGA tutorial, all of them tell you to do this. I went back and I looked for specifically beginner FPGA tutorials, and all of them it's like step 1, create the project file. Step 2, make a hello world gate. Step 3, specify your timing. Step 4, put on the FPGA. And I just didn't know that. I just dove in when I got my FPGA and just totally missed that, which was stupid. But yeah, so then I came home and I actually looked at this, and I can actually pull. Well, I don't have Quartus running now because I had to restart my machine due to network issues. But it turns out I went and I looked at my project, and of course the timing was specified. Since the DDR controller gives us a clock, it gives us a memory interface, and part of that interface, so that we can actually read and write from the memory, is a clock, and says that all the interaction you do with this bus needs to happen with this clock. And so I actually just drive the entire xenowing console off of that same clock so that I don't have to cross any clock domains or anything, and it makes it all really simple. And that's not an issue at all. That actually totally works fine. And luckily for us, because that clock exists as part of that interface, part of the generated IP for the memory controller also specifies that clock is a valid clock, and it specifies the properties of it. So it wasn't that I wasn't specifying that. The issue ended up being, of course, that the timing wasn't being met. And so what that means is essentially that you have a couple registers. I'll actually paint this. The issue is that if you have a couple registers, so for example, that's where I am. Okay. You have some register and another register, and you have some stuff in between. So we'll call this A, we'll call this B. And A has got a data in, and it's got its Q output. We call Q for some reason. I don't really know why. And then this is going to go to this data, and then that's going to have a Q as well. And both of these have a clock, which is usually a little triangle. This is going to be our clock. So the issue with timing is that what happens is that whenever the clock comes here, we get like a rising edge on the clock, which we'll assume it happens at roughly the same time. It actually doesn't, but it doesn't matter because the math all works out the same anyway. As soon as we get rising edges of the clocks here, then Q will match D. That's what it does. This is basic flip-flops. And what happens is that these signals, though, they don't change instantaneously. So when Q matches D, it takes a while for that value to kind of propagate from A.Q to B.D. And this is called propagation delay. It's just a natural property of the fact that electrons are moving or not. And that's just something that we have to deal with. The nice thing is that the tools will just kind of deal with all this for you. You say that, okay, well, these are both clocked by the same clock signal, and if the tool knows that the clock's going to be 150 megahertz, then it will lay out everything such that this propagation delay isn't a problem. If it's unable to do that, however, then this path will actually be too long. And let's say this data was supposed to be ready at this when this rising edge got here, but it actually only got to maybe here. That's obviously a problem, because then this is not going to see the correct data. And that's actually exactly what was happening. That the data that was coming out of here, there was a way too long path between a couple registers in my design. And in particular, it was from the inputs to the register file to the inputs of the memory bus, I think is where the long path was. And it was arriving where it would have been like 2 or 3 or I think it was 2 cycles late. So it just ended up this big path from the inputs to the register file all the way down through a bunch of my CPU to that. And so what the tooling was telling me is that these paths were too long, and it couldn't actually satisfy the constraints I had, because my design was essentially asking too much at this speed. So 2Crypt says, couldn't you just slow down the clock and the errors go away? So yes, that's absolutely one way to do that. However, slowing down the clock in this design would mean a lot of things. It would mean that obviously our CPU would go a lot slower, and then our GPU would go a lot slower. I didn't really want to do that, but that could have been an okay way to do it. I also would have had to regen the memory controller. I didn't really want to do that, because we're going to have enough latency at this speed as it is, so I didn't really want to change any of that. Another thing you can actually do is you can specify what's called multi-cycle paths, and to say that, well, it's okay if this path is really long, because B isn't going to expect A's input until 2 cycles later. And that's fine. But that design doesn't seem very... It seems really fragile to me when we don't need to do that, especially if we have a simulation-based workflow. I would like everything to still be single cycle. So the other way that you can do this, this is a very basic concept, is just pipelining. So we have another register here called C. And so now with this, the data can get from here to here in a cycle, and it can get from here to here in a cycle, and then we have no issues. Now, of course, what that means is that now it's taken us 2 cycles to get the data where it needs to go, but now we're at least being explicit about it. And then we can kind of design around that as a constraint. And then also this will work the same on our FPGA versus in our simulator. So that is actually why I ended up splitting up these stages. It ended up being that there was a long path with those registers, so I added the register wait stage so that we could load the registers. The data going through the register file could have an entire cycle to get from the inputs to the outputs of that stage. And then once I finished that, then I still had a long path between my instruction register and something else in the memory controller. And so that's why I split up the execute and memory stages as well. So essentially the same solution worked in both of those error cases. And the downside now is that we ended up with 2 more stages than I would have liked. But it actually works. So that was nice. Or to Capo said, are you working with anyone on this system? No. This is just me. And that's fun. So this one was reduced. I think actually the way that this works, I might be able to put the registers on this particular kind of memory after, like on the outputs and on the inputs. So it might actually be that I'm able to fold this into the decode stage as well, but I haven't looked into that. Maybe it's possible, maybe it's not. Something to explore. So I want to do that later, but so far it just isn't something I'm worrying about. And everything seems to work. Everything that we know of that I've tested explicitly does work, and I'm happy about that. Of course I write so far because who knows what goes wrong later, but the big lesson there is just always check your timing. That's very important. I didn't know that you could, or that was something I had to do. It didn't. My tooling didn't yell at me in bright red enough, so I didn't notice it. But it's definitely a problem. Loader K-Ball says you can use the falling edge to write to registers. Yep, but then I guess that's kind of almost like a separate clock domain. So I guess you could do that. Wasn't something I wanted to explore. But the most important thing for me is that then I felt a lot better about the CPU. I feel like I can trust it a lot more. It's a lot simpler, and it's something that I can leave it alone for a bit. Like I can kind of trust this for now. And I know that if I ever see any spooky stuff later, or actually I know rather to, before I put my code on the FPGA, I know to check the timing. So now I want to talk about my Python HDL, which is called Kaze, which is wind in Japanese. This is probably the 5th version of like an HDL that I've kind of tried to come up with just for fun. I like compilers. I like making languages, something I've always done. And doing something for an HDL I always thought was really cool. I just liked the idea of having my own code running on my own console that was described in my own language. Just seemed like a cool stack to have. But of course I keep trying to kind of like start this project, and then I get a little bit into it, and then I just don't really like where it's going. Like I kind of just start with different designs of the language, and I don't know what happened. It's just in the last week it just kind of clicked, and I knew what I wanted. So I just kind of started it again and then got really excited about it. So system Verilog is really nice to know. It's a bit verbose, and it doesn't really match my mental model, as I mentioned earlier. Again, big disclaimer, I'm not an expert at this field, so I might just be up in space on my own little tangent that might be completely useless, but who cares? I'm having a lot of fun. Again, I always wanted my own HDL, could never decide on the design, it just clicked. So I prototyped kind of the main ideas in Rust and Python, and actually the big reason I didn't do Rust is because if you want to model these kind of circuits, it makes a lot of sense to have them as like mutable object graphs, because you're kind of building the graph progressively with your language, because you might have this register, and then maybe I'll do like an inverter out of here, and then maybe I'll hook that up to another register. But then the big important thing about this is you often have feedback. So maybe this Q goes through some logic, and then this goes back to the D on A again. And this is a very useful, well, this right here isn't a useful circuit, but this pattern comes up everywhere. So you need a mutable object graph with cycles in it. And in Rust, that's like the worst thing you can do. That's like sacrilege in Rust, to model that. I mean, you can do it with like IDs and runtime checking or whatever. You can do it with some cells. You can do all this kind of stuff. But it was just easier to do it in Python, and more natural to do in Python. And the biggest thing that I think I would have gotten from Rust is type checking and compiler help. Well, I'm not really doing that complicated logic here, so I don't really need that much compiler help. I'm not even really doing that difficult type checking, because I can kind of make my own signals, and the signals have a number of bits, and that's kind of mostly the only type checking I actually want, and that I'm going to have to do at runtime anyway in Rust or Python. And I think, to be fair, I think if I continued looking into this in Rust, I think I could find some nice things. I think procedural macros could be used to great effect in making some of the procedural stuff. I think macros in general, actually, with Rust could probably hide a lot of the syntactic things that I didn't want to deal with. So I'm kind of just like avoiding the issue, and it seems to be okay. So I'm pretty happy with this choice so far. But yeah, we'll see. Anyway, I'm really liking it so far. The main kind of idea with the language is that I wanted to describe modules as registers and combinational logic. That's kind of what's going on in my head, is that I can see the registers and I can see what's between them, and that's what I want to write. And yet I find when I'm writing Verilog, and this might just be, again, my own, maybe I'm just totally wrong here, but I feel like with Verilog, it's very disconnected from that. With Verilog, you, let me give it a little bit of an example here. Let's say I want to describe a register, and a register in Verilog again is like, or a register generally, you have this data input, and then your Q becomes your data when clock rises or falls or whatever, when there's some edge. And with this kind of behavior, is if you have a few ways to describe that. You can say, I want a register. So I kind of want, let's say I want a 1-bit register. Then I want to say reg1. That's what I want from my register. Whereas in Verilog, what you do is Verilog is sort of based on, you have these signals, and then you can sort of describe when they change and what they're sensitive to. So in Verilog, you'd write something like logic, so let's say A is my register. You would say like logic A, and then you would say something like always at, where's my at symbol? There it is. Always at the positive edge of my clock, you would do begin and end, and then you would do something like A is something. A is not A. Or that kind of inverter. And this right here, you kind of describe, you sort of make a signal called A, and then you're describing the behavior of A. And because A has this behavior that it will only change when you have an edge of when this changes, then Verilog will infer that what you meant was a register. Right? And I don't think there's anything wrong with that. I think obviously this is a good way to work. There's a whole industry that uses this for a reason. But this seems a lot... I know this is a very contrived example, but this seems like a lot more than what I want to describe here. And there's some really subtle differences here that can be really dangerous in Verilog. So, for example, what if you do this? If I have some sort of input reset in my module, what if I did if not, or let's say it's a active low. It doesn't really matter. Let's do it this way, actually. And then we can do something like this. Actually, we'll do it like this. If not reset, then we'll do this. This actually will not infer a register anymore. This will infer a latch, because what about this other case? We actually haven't described enough information for this to infer a register, just because of the way that this logic works. And again, like this is kind of basic Verilog stuff. Like this is easy to work around because you can do something like this, where you do A is 0 or something. And actually, I think in that particular case, we might actually be okay, because A will just keep its value after this too. So it might actually be fine that would have still generated a register. But my point is that with Verilog, you're kind of describing the behavior that you want to happen, and then it will sort of infer the structure to match that behavior. Whereas I actually wanted to write the structure, and then I want to infer the behavior, if that makes sense. Now, that seems to work really well in my head. So, for example, I can make, in the language that I want, this happens to look like what my actual language looks like right now, but this could be anything. I want to do this. And then what this says is A is a register, and I want to create a new signal that is an inverter out of A's output. And then I want to drive A with that again. Then I will do drive next with B. This is something I could do, or I could just put this in line, for example. And this to me actually gives me that same kind of behavior. Here I've made a register, and here I've done some feedback where I drive the input of that register with the output of this register through an inverter. And again, Verilog, this is not hard to describe in Verilog, but it's just a little bit further than what I'm thinking. So that's exactly a weird constructor. It's kind of abstracting away some of the hardware thinking in my head. I've talked to a couple of my colleagues about this, where this is all second nature to them because they've worked in Verilog for so long, but they also said that they did initially have a hard time kind of understanding that like when you're writing Verilog, you need to be thinking about the behavior that you want to describe, but you also need to be thinking about the hardware that's actually going to infer while you're describing it. And to me, I'd rather focus more on the hardware first and then maybe add some things to help me with behavior, rather than the behavior first and then maybe add some things to help me with the hardware. Again, big disclaimer, I might just be talking out of my ass here, but that to me is the philosophy that I want when I'm trying to learn about this hardware. And to me, having a language like what I show here seems to be better for me than Verilog or VHDL. They're in the same kind of camp to me mentally. So Halo Decabo said that other example would have added a clock enable, so an and on the clock, which may or may not be what you want. So yeah, Mr. Liquid says, does this compile to Verilog? And yes, it does. That's a big thing because you still need to interact with all the other tools. So my language does compile to Verilog. By the way, everything I've mentioned is open source. I will show you guys the actual file. It's just a Python file now. But maybe I can show some simple examples while I'm talking about this. Or maybe I'll go to my slides first. But yeah, so this is what I mean by kind of opposite. Again, I don't know if this is a great idea, but there are a lot of other frameworks that seem to be doing this. The reason I created my own is just because this is something I'm exploring and I'm having a lot of fun with it. I don't expect people to use this. I don't expect to make a product out of this. It's just something I'm doing for my own enjoyment, and I'm liking that. So I think that's fun. Dark Second said, do you recommend learning Verilog before a higher level HDL? Definitely. I mean, you need to be able to read Verilog no matter what. And being able to write it obviously helps trying to understand what these higher level ones are doing. again, I admit that my experience with Verilog probably isn't enough to maybe even answer that question. But in my experience, I'm enjoying working with my higher level one more, but I'm also glad that I knew Verilog enough to be able to make that and to be able to figure out what it was I didn't like about it. And it took me a long time too to realize that this is what I wanted. And maybe it's not what I want next year. We'll see. But I'm happy with it. One thing though that Verilog has that I also wanted, and I can kind of I'd rather show some examples than kind of illustrate the problem first. But let's take a simple one. So for example, uart.py. Maybe that's not the simplest. Obviously, also my language isn't done. I'm just kind of throwing it together. So like, there's a lot of patterns that I still want to have. So Verilog has like switch case kind of statements. I want something like that as well, but I only have ifs right now. Ifs with no else. It's kind of cool how I made those work, but we'll get there. So in a way too, like this language is kind of gimped, just because it's so early and it's just something I'm playing with. But I don't know. I'm enjoying using it. That's all that matters. I feel like I have to defend it, but really that's the bottom line. Let's see. What's a simpler state? So this is my CPU. This is the almost all of it. I think I still have the ALU is still in Verilog, which I also simplified to match the decoding of risc-v more. And the main reason this one's still in Verilog is I haven't implemented all these operators yet, but a lot of these I have. So I think it's just the shifts actually that I need to do, and then I can do this. Also, I kind of want this case construct, so that's still in Verilog. The register file is still in Verilog. This is definitely something I would like to be able to express in my language, but again, in a lot fewer terms than this, because this is written a very specific way that gets Quartus to infer that I wanted a block RAM here. And it would be really nice to be able to just say I want a block RAM in a given size, and then it would have generated all this. Again, it might be a really contrived case, but that's a case where that would have helped. And then there's the very top level code, which is still in System Verilog, because I actually haven't added module instantiations in my language yet, which should be more or less trivial. So at the very top level of my CPU, it just instantiates a bunch of modules and it adds a couple more registers, but I also want to move that into my language. So it basically just puts a bunch of stuff together and does a bunch of plumbing, and I also hope to make that plumbing a little bit simpler. But anyway, CPU.py has all of the rest of the stuff. So there's this instruction class, which is again another big thing that you want a lot in hardware design is metaprogramming. And I think System Verilog's adding more and more to that effect, but it's also just really helpful to be like, I can create an instruction with this source that's 32 bits, and then whenever I just want a piece of that, I can just do this, and it'll just take those different bits from that source. Kind of nice. But yeah, so my program counter register, for example, this is a program counter register module, so I make a module. And I have its internal value is this 32-bit register with this as its initial value on reset. And then I take the value, and its next value is either going to be its current value or a 32-bit input called write data's value. And whether or not it uses those depends on whether or not this write enable is another signal that comes in. So not terribly difficult. And then I just output the value of that register on output code value. So this to me is a nice way to write that. I have a cycle counter register and instructions retired register. And I think these are almost identical, except this cycle counter always increments, and then instructions retired has an increment enable on it. Because you only want to enable this at the end of an instruction, whereas this you want to be enabled all the time. And again, these reset to these other values. Then the control one. So this is where it would be nice to have like a case thing, because here I have a bunch of these ifs. And the way this if works is kind of fancy. I want to gloss over it for now, and it might be a really nasty thing I'm doing in Python. In fact, I know it is because it relies on some C Python behavior and whatever, but it gives me a syntax that I like. And while this is just my own playground, I'm okay with this. Essentially, I can make this signal called next state, and then I have these ifs that use this Python with syntax to actually capture all of the locals as it goes into the with. And then as it goes out of the with, it looks at all the locals that have changed. And first it ensures that you only changed a bunch of these signals. And then what it does is it actually, instead of having the signal be this new value, it puts a mux here where it either selects the old value that it was here or the new value that it is here based on this condition. So you kind of bake the condition into that. And so you've kind of inverted the way you describe that. That's something that I just stole directly. Like Verilog had a syntax for doing this with blocking statements and if statements that I really like. So I just kind of tried to implement that, and I actually quite like that. I think Megan has like the same thing, so I'll probably just use that for the next one, but I thought that was pretty cool. Yeah, Rust proc macro could also totally do this. This isn't that useful with just one signal here. It's usually useful when you have a combination, and when in these different like if statements you will do different signals. That's kind of when you want it, and they also nest, which is really nice for some of this stuff. So a lot of these stages too are just purely combinational stuff, and then this is just so much less typing than it would have been in Verilog. So here my instruction fetch has an output signal called ready, which just takes the bus ready and puts it through. It has a bus address, which is just these bits of the program counter. In fact, it's 30-bit program counter because it's a word address, and I just put that out on the bus. And then the byte enable is just always high in this case. The reason why we have a byte enable, we actually may not for this stage because we're just going to mux this with the memory stage anyway. But yeah, these essentially all the things on the bus are everything's word oriented. But then within that word, you can enable or disable different bytes if you only want to read or write a couple of them. And mostly that allows the memory controller to kind of optimize stuff, but it really helps when you want to do just write part of a word. The controller will just kind of take care of that, which is really good. But in this case, we always just want all 4 bytes of the instruction word coming in, so that's just tied high. And then read request line that goes out of it is just whether or not this is enabled. So like this stuff just makes so much sense. Then decode is also trivial. Execute obviously is the most complicated one by far. In fact, I think I don't even have an explicit state for the register weight because I just I think I just have a state for it up here, but I don't have a stage, which makes sense. Execute is the thing that's doing like the vast majority of the decoding. A little bit of the decoding is done in the other states, but that's just the way that the outputs of those states are tied into some inputs of some registers. And yeah, I mean, this is all fairly basic stuff. Like it's a lot less code than my other CPU. It might be hard to see that, but it definitely is. Because I tried to do a lot of things like I tried to have like as little logic that's specific to a given instruction as possible. So I think these 4 instructions are the only ones with like very specific kinds of logic, and then like loads and stores as well. But even then, like most of the stuff for loads and stores is the same. You just have to determine which bytes are enabled if you're doing load, and then whether or not you actually will issue the memory thing or issue the memory reader write, which is determined in the next stage anyway. And then the loads, this determines the address. So this actually should also have stores here because the addresses and the byte enables are the same for loads and stores. So it also like it does that logic for both as well, which really helps. Lord de Capo says, do you have a link to your instruction set? This is a risc-v. It's a RV32i. So it's really basic. I didn't design the instruction set on purpose because I knew I wanted to write a lot of C, and I didn't want to write a C compiler. I wasn't that interested in that part for this project, so I wanted an off-the-shelf architecture that was as minimal as possible. So just the base risc-v instruction set was a good choice. And then loads again just will enable these different signals, and then the stores as well. Yeah, could actually do Rust. At least Rust with no STD should work. So that's pretty cool. But I still think I might need to have my own build for that just to produce the right. Well, actually, I could use Rust C directly and then just get object files and then have my own linker script anyway. Then it wouldn't be that bad, I guess. That'd probably be the way to do it. I mean, that's kind of what I'm doing with GCC anyway, so that should just work. That'd be cool. But yeah, it's mostly a lot of this logic just gets kind of flattened. There's a couple of cases here where my language, it would be nice if this were more descriptive. Like these are all just equality checks for any of these values. And this could be like a switch case kind of thing. But again, the logic still isn't very big. Like I think I wrote half the code for this or something, and that's with a lot of the extra. Maybe with all the interconnects, it ends up being more code anyway. But that's just because I split everything up into different stages, and then you have to describe how those are connected together. But yeah, the memory stage right now just is a bunch of registers, and this actually violates the way that I've implemented most of the CPU, because typically I've implemented the stages as purely combinational logic and then registers in between. And I think that's the better way to do it. But in this case, since I was trying to fix timing, and the quickest way to do that was just throw all these registers, was to write them in this language, and then I just threw them all into the stage. So that's something I would like to split out as well when I start doing the top level code in this as well. But I just haven't done that yet, because this was all like days ago. So we're seeing in this as real time as this can get, I guess. And then the write back one has to do some stuff about whether or not. In fact, I think. Oh no, I actually decode the parts of the instruction again. Maybe I'll change that actually. Because, for example, these loads. Well, you do need to know if a read or write came in, and you need to know which bits were there, but maybe that can just be taken from the output of the previous stage. That's probably the case. That's probably better. So maybe I'll change that as well, but it doesn't really matter too much. Again, we meet timing, and this CPU is fine. So I don't know, 400 lines of Python plus some plumbing, which ultimately this would probably be, even if we doubled this, right? Even if this was 800 lines of Python for a risc-v CPU, I'm still pretty happy. And I think it's about that. Including the system Verilog for all of the interconnect between the stages. It's another 300, and then we have the ALU and the register file. Yeah, not too bad. And I'm pretty sure this is correct. I haven't tested all the instructions here explicitly. I haven't found any bugs yet. There might still be some in there. I would still like to explore some formal verification stuff, hooking this up to these risc-v tests that people have made. Which would be really nice. Another advantage of using like an existing architecture is that we can sort of plug into all of that ecosystem. So it would be really interesting to do that at some point too, but haven't done it yet. Maybe I won't. It's kind of fun to not actually. But yeah, so that's a bit of that kind of language that I've done now, and actually all of that language is implemented in this Python file. And this is like, 550 lines or so, a little bit more. And it will generate all of the system Verilog, and also has all the stuff for like the syntactic sugar, you have the main data types are actually really simple. You have a signal, which just has a number of bits. And then just like an error helper here. And then you have a source, which is a signal, and you have a sink, which is a signal. And within the context of a module which has inputs and outputs, the inputs act as sources and the outputs act as sinks. So the whole thing is just like almost everything is a source. So like high or low is a source that's either 1 or 0. And then you can do equality on that, not equals on that. You can do like and OR operations on that to sort of combine them. And this will make sure that they're like the right number of bits and that they're compatible. And it will error as soon as you create those, so that you get the error on the same source line as Python in Python as you would have if you had done that in Verilog or whatever. And then you can like pull a single bit out of that. You can pull a range of bits out of that, and it will do the range check and everything. You can repeat a bit a number of times, or repeat an entire source a number of times, which is really helpful. You can concat sources together, which is kind of another way to. There's a concat function on here, and then there's also a concat, just depending on if you want to write it infix or prefix. And that's mostly it. A register is a special case where it's a source and a sink, because its next value is the sink, and then its current value is the source. And that's like the whole model. Everything else is just combining those things together, which I think is really interesting. And then the only other thing that this has is that if thing. There's also a ternary expression, which is essentially used for muxes, because you need some kind of conditional. And I chose to implement it as a ternary in system Verilog just because it was easier to kind of read the output, which you still have to do from time to time. And yeah, this if thing, again, it just does that like local stuff and then builds muxes, and will catch some errors. So it's not that much code. It does do some kind of nasty stuff because you're not supposed to be able to modify the locals like that, but we can do it, and I'd like to take advantage of that, so that was kind of fun.
And then there's the code gen stuff that kind of goes through this. So it really isn't that much code. And then, for example, this all goes into this generated.sv file, which is part of my build. And then this is the equivalent Verilog. Now, a lot of the cases, so I think this is the execute stage. I end up with a lot of these sort of intermediate nodes. And this is just because the way I've described it, so in Verilog, you have something where you can say, like, let's say I have some register, which is 32 bits. And then later I want to just pull out, I don't know, bits 6 through 3. And say something else is that. Well, it turns out you can't do that you can't then pull a single bit off of that and then concatenate that with 32 lows and then pull a specific bit off of that. Like these don't chain as I would like them to, but I would like them to kind of be able to do that. So in order to do that, you have to generate these sort of intermediate nodes and then pull bits off of them like that. And again, this is a lot more verbose than it could be because this is just output code. But that was just an easy way to do it, to get it to compile and be able to support that kind of syntax. So a lot of these nodes are just intermediates that I'm going to pull bits off of. And it does this like pretty eagerly when it generates these. To generate better code might be a goal. I don't really care because the one concern that I did have with generating a lot of code like this is how does the tooling deal with that? That was kind of my big concern, but it turns out it does just fine with this. It simplifies this quite a lot, so not too worried about that. Mem stage is a bunch of registers, so here you have all these registers, and this could be written a little bit differently too. So like here we have this node next that's assigned down here, whereas this assignment could just well gone here, and then we would have needed this node next thing, that kind of stuff. Also, you'll notice all my resets are synchronous. That's something I would like to toggle because I think most of the design here will use synchronous resets, or at least asynchronous resets with synchronous deassertion, which is something I've been reading about a lot that I won't get into in this stream. So I might want to change that. But again, then I can just change it in the generator, and then it's all kind of solved. I'm not too worried about wasting gates because, again, these nodes, like this will go through an optimizer after this in Quartus. So it's not like I'm using more gates by having this pattern. For the synchronous resets, I might be having some additional gates, but again, there's ways around that I'm probably just going to change in the generator, and then it gets fixed everywhere. So that's kind of nice. Yeah, and then we have since this generates everything together into one big file, all the modules that I have. There's also, here's the code for the LED interface, the program ROM interface, a bunch of just pieces that I've replaced with the Python HDL now. The system bus in particular, which does all memory mapping, is a longer one, but it's mostly just these ternaries. So I'm making more work for the input stage of the next compiler down the chain, but it really doesn't matter. The compile times haven't exploded or anything. They haven't even gotten worse as far as I can tell. And again, what's really important, if we go and look at like the RTL view for my project, we'll see that this is actually pretty good. Other than things like being named node whatever all the time when we look at the RTL viewer, I'm thinking about adding like a tagging mechanism where you can just tag the ones you care about, and the other ones that might just generate really short names so you don't have to look at them. Not really sure. That's one of the disadvantages of using a generator. And it's, especially in embedded language like this, because you either need to take strings as arguments everywhere to like give them nice names, or you just decide where you want to do that. And I'd rather just decide where I want to do that, and then, but I haven't actually implemented that. But if we look at this is the top level thing, there's the xenowing itself, which is the main console. And this essentially just has a memory interface, which is actually like, I think this is the Avalon interface, which is what we get from the DDR controller. And it also has like the output for the LEDs. It has a program ROM address. The program ROM is separate from this. It has a UART transmitter line, reset, program ROM input, clock, and then more stuff for that bus. That's basically it. And then inside here, it's broken down into the LED interface. And so a lot of these interfaces, like the LED interface, just hooks up because we have the CPU over here. And the CPU pretty much only talks to this system bus. And then this system bus is what does all the memory mapping and fans everything out. So we have a LED interface, and then we have like a UART transmitter interface. And this doesn't have the UART transmitter in it. That's actually over here. This just is the interface between the system bus and like a standard UART transmitter. And I like that approach because it keeps everything kind of separate. You can design a UART transmitter without having to interface with the CPU, and then you can design the interface that glues them together. Same with this DDR3 interface. Like the CPU doesn't have to know what memory is, just has to know about a certain kind of bus, and then everything uses that same bus internally. So the CPU, again, this is all generated with my HDL. This doesn't look too bad at all. A couple registers between the different pipeline stages. The pipeline stages don't end up in order in this view, but that doesn't really matter. Can I zoom in here? So in here we have, for example, cycle counter, instructions for tired counter. The execute stage is the really complicated one, but even this is a lot simpler. Again, I don't know if you guys remember or if you guys watched the old streams where I had the old CPU, but even if I go in here and I start expanding all of these, so like the decode stage, let's open that up and we'll zoom out a bit, and decode is just a pass through. So some of these get so simple. The write back stage, we'll expand that, some muxes. And let's see, the register file, we'll expand that, and this should just end up being a block RAM, so this shouldn't be much at all actually. Also, by the way, when I was having timing issues, I actually experimented with replacing a block RAM with a bunch of registers, and it was way slower, which of course makes sense, but it's something to try. The ALU is actually still somewhat complicated, but that's because it performs all of the available ALU functions, and I think it simplified the logic a bunch to have essentially these 32 boxes, and then all the inputs go through different gates depending on the decoding of the kind of instruction. So just like the other one previously. So actually, if we were to more accurately compare this with the old CPU, this module hasn't really changed much, except it's actually gotten simpler. But that also was a separate unit, so we can keep that folded for the sake of this kind of demonstration. Cycle counter, some of these are just really basic counters. I think the program counter. And let's see, go over here to the execute stage. And that's, again, the more complicated one, but still not that bad compared to the old CPU. ALU we're going to leave as is. And then we have what's left. The memory stage, which right now is just a bunch of registers and a couple muxes. And then we have the instruction fetch, which is just a pass through. And then the control logic, which is the state machine. And that's basically it. So all this together, so it even inferred my state machine. And it inferred this much nicer looking picture of a CPU than what I had before. So this is generating perfectly acceptable code as far as I can tell. And I'm quite pleased with that. So there it is, a risc-v CPU. And we can even put in the, just for fun, we'll expand the ALU. There it is. Not too bad. There's parts of this that could probably be simpler. Like I said, I just got this working, so maybe I'll take some optimization passes. But I don't need to. Pretty happy with this. So that's pretty cool. Anyway, again, I'm well aware that this might be a bad idea. It might just be my inexperience showing when I'm working with this. But I'm really enjoying making this a language, and I'm enjoying using it too. So all in all, it's made the project more fun for me. That's all that matters. Pretty happy about that. Anyway, so what's next? So I think I actually forgot to have some slides in here about debugging the UART, because I actually really like the way that I did that and kind of the flow that I thought of. So what I had done, I want to tell this little story before I move on. We probably won't get to any actual coding today. Maybe we will get to a little probably at the end. But like I said, there was a lot to talk about, and I really wanted to go over all this. So I'm hoping you guys are enjoying this, because I'm pretty happy about it. So let's see. So I had noticed that when I was doing this ROM reload, the biggest problem is that I didn't know if it was my UART receiver that was bad. Spoiler alert, it was. I didn't know if it was some timing things that I had done, because I'll actually go over this in the RTL viewer, because this is actually part that I don't simulate. I might move this into the simulator later, but for right now, so I have this xenowing itself, and then this is connected to the program ROM and like the DDR memory, and it also has some inverters for the LEDs, and then just goes to the very top level stuff. But this program ROM is actually a RAM. And the reason why it's a RAM is, again, to support ROM reload. So from the xenowing's perspective, it just sees a ROM. And I want to keep it that way. I don't want that to be writable. Maybe I'll change that later because this ROM ends up has a lot lower latency. This has 1 cycle latency versus the DDR memory, which has like 12 cycle latency. Maybe even more. I don't actually remember. It's been a long time since I looked at that. But essentially, this could be like a fast RAM too. So it might actually make sense to have the xenowing be able to write to this later, or at least another segment of memory. Not entirely sure. But in any case, this is a RAM. And the way that we're able to reload this is I have a UART receiver here. This is my new one, by the way, which again is a lot simpler than my old one, and works. But the UART receiver goes into this ROM loader. And the ROM loader, what it does is it just sits there and waits. It's in this idle state. And as soon as the UART is doing UART decoding and then sending out bytes, so it has this data. You guys definitely can't see that, but it has as output this data, this 8-bit value, and then a data ready. So as soon as it gets a pulse on data ready, this will be high for 1 clock. Then the ROM loader knows that it's got a new byte. And so the ROM loader will sit in a state where it's just waiting to see data. And then the first 4 bytes that it gets, it interprets as a length, and then it starts taking every byte after that. What it does is, as soon as it gets that length, it turns on this system soft reset, which actually holds the rest of the system in reset, which is also why I want to do synchronous resets for that. So it holds the whole CPU and everything in reset. And while it's doing that, it starts writing to this memory. And then once it's written that many bytes, then it will go back to its idle state and then take the system out of reset. And that together works really well. So then we're able to, from just by sending a bunch of stuff over serial, we send a 4-byte length and then we send a bunch of bytes. We're able to rewrite the entire ROM, and that takes almost no time. That's essentially instantaneous. And I'm really happy with that. But of course, the big problem with that is that the initial UART receiver that I wrote was really bad. And I wanted to be able to improve this, and I didn't really know where to start. But I also knew that I didn't want to have like a really slow debugging cycle on the system, because that's something I had a lot of trouble with last time. So when I tackled it again, the first thing I wanted to do is see, well, like, is my transmitter good? Because maybe I can make this kind of loop back where like I'll receive data and then I'll send it back. But of course, I don't know if my receiver or my sender's bad. In that case, it could be any part of that chain that's failing. So I wanted to try and isolate it. So I isolated the CPU and the transmitter. And what I did is I wrote some code to this little PRNG here, which is a little LFSR. And so this is essentially generating a big random sequence, and it's just going to generate a bunch of bytes and then write them all to the UART one by one. That's all that this is doing on the CPU on the FPGA itself. And then I have a almost equivalent program, or the opposite program, which is this LFSR check here that I wrote in Rust. And it's just opening a COM port and setting the same baud rate. And then it's also reading a bunch of data. And for every byte it reads, it generates the same random number and checks. And then it just keeps track of the total versus the expected. And I let this run. I went out with a bunch of my friends the other night, and I let this run the entire time I was there. So it ran for about 4 hours. And I came back home, and it had transferred about 150 megs with 0 errors. 150 megs in 4 hours is obviously not an impressive data rate. This is not a large number here, but that to me is something that I can generally trust. So I felt good about the transmitter. And so then what I did is I hooked up the transmitter into my simulator. And then what I did is just plotted it out. So I plotted a couple different signals. I want to try and show an image, but not show all of it, because we're kind of going to get to the thing here. So essentially I plotted where I could see that this was a write request to the UART transmitter, and then this was what the data was. So you can't actually see the pulse because the cursor's on top of it, but there's a small pulse here, and then some changes here as the write data is changing. Anyway, at this cycle where this read is issued, we see that AC has been written to the UART transmitter. And then we see that this is what it looks like. This is what the UART for the byte AC looks like. We have our start bit, and then we have the byte data, and then we have our stop bit at the end over here. So like really basic. UART is not a complicated protocol, but we knew that was valid, right? Because I had tested that. So then what I did is I just wrote at the top level of my code, I just said, okay, I'm going to write a new UART receiver, and I just instantiated that right next to the transmitter and just had the transmitter feed into the receiver. And then just in the simulator, I didn't even run this on the hardware. I just ran this in the simulator a bunch. So then I hooked up the, let's see here. This was the RX, which is just directly from the TX. And then I hooked up a couple metastability flip-flops. So this is just a couple cycles delayed. And then I made a clock for the receiver that was 4 times the rate of the sender. I thought a lot about this rate, by the way, and Nyquist Shannon said that tells me that this rate should only be about twice the rate of the sender, but because we might be a little bit out of phase with the sender, that might actually be slightly faster than what we want. And so then ×2 wouldn't work, but ×4 should be okay. Maybe I'm not thinking about that the right way, but anyway, I'm only doing 4 times the clock rate of the sender for the receiver. And then what I did is I just kind of tweaked this implementation, because then I implemented the receiver and I just tapped onto the data that the receiver had internally and then the receiver's data ready signal. So for the same byte, you can see here's where the read is, or where the write is issued. And then some cycles later, the receiver has said, yep, I got a byte and here's what it is. And you can see that the data matches. So I just did that, and it was so obvious to verify. And like I had some of the timing wrong on some of these pulses, so I was like tweaking the value, but then I was iterating with the simulator workflow. So it was extremely quick to get this working. I probably did this in half an hour or something. And then by the time I hooked that back up into the rest of the system, the ROM reloader just totally works. So extremely happy about that. And I think that was a really good way to debug that. We could verify that the sender was good, which is the sender we had complete control over, and we can run in our simulator. And then we can make a receiver that receives that, and then ideally that's close enough to what the actual chip that I'm working with sends. And it turns out that was totally correct, that actually totally solved that problem. So I did want to talk about that because I thought that was really fun. Like in the last week, I learned I need to check my timing, and I learned how to do that. So I was really happy about that. In fact, I will actually show you something else that is bad. So this is the result of the last time I compiled this. I'm not going to compile it again because it takes 5 minutes, but this is the xenowing itself, and like we were looking at the RTL viewers, so we could see that that's what the machine was. But I wanted to talk about the timing analysis actually, because if we look at this, let's say view report here. So this would have been like the report for the compile. This is Quartus, by the way. This is Intel software. And this is Quartus Lite because I'm not going to pay a couple $1,000s just for my personal project per year. Pricing model makes sense at enterprise, but not for me at home. Anyway, you'll see that this is the timing analysis that happens at the end of the chain here, and you'll see that a bunch of these are red. And so what these are different simulations at sort of different extremes of like the manufacturing process or the temperatures or whatever. And in the fast model, which is kind of assuming best cases, we don't have any errors. So this is not red, but this stuff is red. And so what I'm actually going to show you is that this design still has timing errors, but I want to show you where they are. So this is what it looks like. Let's go ahead and look at this. So this is analysis of the setup times for some kind of path. And what this shows us, if I can make this a little more palatable for you guys, this shows us a bunch of paths that actually don't meet timing. And in particular, it shows us how it doesn't meet timing. So for example, this is setup time is violated. So essentially it says that there's going to be data latched over here with some clock delay. And we want the data to be ready here. But the data actually arrives late. I think here is where it's okay. And then this red is how much we violated timing. Now, the frustrating part about this is that this is actually within the DDR3 controller, which was generated by Quartus. So the way to fix this would be to try and tweak my parameters for my board, which also came from a tutorial from the board, and then regenerate it. And maybe just updating all my software and regenerating this again, because I did this last year, but maybe that just works. So this actually shouldn't happen. I shouldn't be violating any of this timing like this. And that's really annoying. So maybe this bites us in the ass later. But this is like, in this case, we're violating, this is negative 1.276. I believe this is in nanoseconds. So it says it's that many nanoseconds late. And again, nothing actually goes wrong with this. So I'm not entirely sure about this. And I don't know what part of the controller this is, other than obviously it has the name here. It says user MR address. But again, it's from this is between two nodes of the controller. So I need to regenerate the controller and see if that helps. But again, we don't see any actual issues with this because this is testing for extreme cases. So this is bad. You normally don't want to see this, but it's a good opportunity to also show you guys what this looks like, because you get these nice timing diagrams. And the timing issues that I had in my design before I added those initial pipeline stages, this is like 1.2 nanoseconds off, where I was like 6 to 8 nanoseconds off. So like entire cycles were just lost when I had those timing issues, which now those aren't a problem. But now I see these, but they don't seem to cause any problems. So maybe I dig more into this and fix it later. For this application, I don't need it to be bulletproof, but this is still a good thing that we might want to worry about. Or it's a good thing to worry about, maybe. But right now, we seem to be okay. So we'll maybe get back to that. Anyway, I'll hand wave that away for now. So the next things I want to work on are, I want to have better UART management on the PC side, because I can hook up PuTTY and then that will listen on the terminal. In fact, what I will do is, let's see, I'll just pull up PuTTY here. So I have PuTTY, this is a xenowing configuration. I'll open that, and I can do this. And I think if I just reset the FPGA now, no, it's not running a design that prints any code right now. So let me do this. Let me load the code onto here. Open up the programmer and start. And what we should see is, oh, but we got a bunch of crap. Oh, I know why. So PuTTY complained about this data because this is the LFSR data still. So what I want to do is I want to open up another terminal here and run my dev projects xenowing cd misc rom loader, and I want to run this where we give it the rom.bin, and it will do the reload. Except it couldn't open the serial port because PuTTY's listening to it. This is actually a good demonstration of why I need this. So we'll reload this, and then the ROM reload worked. You guys can't really see it. The device, and actually I think I need to, yeah, now it's working. If I open PuTTY again, and then I'll reset the device again. Reset. There we go. Now we see a bunch of prints from the device. Says we're in main, and then a big long string, and then some stuff about setting initial LED value, main loop time. So the thing is that, so I can print out the stuff from PuTTY, and I can send stuff from Rust, but what I really want is one program that I just run all the time, and then it will print out everything. So it'll kind of act like a terminal like that. It'll print out everything it gets from the system, but it will also, I want it to file watch my ROM file so that I can just sit in a terminal and just reload that. So you just edit the code and run make, and then it will reload everything for me. So that's what I mean by better UART management on the PC side. And then maybe, so I think I mentioned that I might actually have the UART later be used for some other stuff, or I might want to do some basic controller input or whatever. And the way I'm thinking about like an initial implementation for that is to have the UART be readable by the CPU, and then use that for some basic message passing, and then sort of define different kinds of messages that I can have, because then I can kind of build sort of almost a really basic like driver stack. So like I could have a message that says, oh, this button on the controller was pressed, and then I could just keep that state in some global state in the system. And then I can have like a system function that's just like load button. And then later, if I want to hook that button up to something else, then I can sort of replace the underlying software and hardware. So instead of sending messages from my PC, then it would actually come from some other event. But then the interface would be the same. So all my test code would be the same, but then the underlying system would get that from a different place. So I would kind of use message passing for a lot of these kind of features. And like maybe I want to do some file IO and I don't want to hook up storage to this, so that's going to be really messy, but I could do that also through this UART interface. And then it would be really slow, but it would actually work. So I feel like I could get that working fairly quickly and kind of build up a lot of my little system APIs on that, and then kind of replace the underlying implementations with dedicated hardware or whatever later. So I might actually do that because I think that sounds interesting to me. But it also might be out of scope for what I want to do. Because again, the thing I'm most interested in is actually starting to make like a GPU. So I now have enough of a CPU and ROM reload that I can reload programs, and I think getting to a GPU that then I can start prototyping, kind of build, I think that's the most interesting part for me. So that's kind of what I'm prioritizing, I think. Obviously, I want to flesh out some missing features in the Kaze language, like especially instantiations, because then I can start replacing a lot of code. And there's a couple places where I want to have explicit primitives in this language for like blockrams and some other things that I know it will generate code that can infer the kind of hardware that I need. So for example, one of the things that I have in here is a FIFO. So whenever you issue a memory read, the underlying bus is oriented in 8-byte words, whereas my system bus being risc-v and being 32-bit is 4-byte words. And so whenever you issue a read, I issue the read to the bus, and then I also put the lowest address bit into a FIFO, so that when the read comes back, we get an entire 8-bit or 8-byte word, and then that bit we pull off the FIFO so that we know if we want the low 4 bytes or the high 4 bytes from that read. And that would allow the CPU to issue multiple reads, and then we're able to sort of decode which word the CPU meant to read on the way back when the data comes back. So that FIFO, for example, uses a memory internally, so I want to have a primitive language to describe that memory, so then I can describe the FIFO. And then once I can describe the FIFO and I have instantiations, then I can replace all of that. So like that's part of the code base I haven't touched with my language yet. And that's why there's sort of this dependencies. So it would be nice to do that, maybe some switch case stuff, and maybe some like higher level stuff to describe a state machine more explicitly. And maybe sort of hide some of that with some sugar. We'll see. And then I want to move more of the hardware into that language when I have some of that. But I think this is all kind of stuff for making the project nicer and kind of making it nice to work with. But the next goal for the hardware itself is video output. And the particular board I have, it doesn't hook the FPGA up straight to the HDMI output port or connector. It goes through this ADV7513 chip. And this is a nice chip. It handles a lot of the lower level HDMI encoding for us, which is good. But in order for us to send anything out, any kind of video signal out, we have to go through this chip, and this chip needs to be configured for like resolution and some other things. I think actually resolution and that's if it will defer from the video signal, or infer from the video signal. I need to double check that. I don't remember. But we need to at least enable it and like check if the monitor is connected, and if it is, then we need to enable it, and then we can start sending a video signal. And again, I had done that before in Verilog. That was one of my earlier projects on this board, and then just generated some really basic signals. But it was a big pain in the ass when I was kind of doing all that together. And this one I want to do more piecewise. And in particular, I actually thought of a really cool way to do this. What I think I want to do is since we have to set those registers over I2C, what I'm thinking about doing is because I want to have my own I2C bus. I had implemented that before. I wasn't really happy with it. I would love to do it again in my new language. And I think that'd be fun. And it also fits in with our philosophy of the only generated thing we're using is the DDR controller. I'm pretty happy with that too. That's where I'm drawing the line. I want to keep it there. So the problem is that I want to do like an I2C master, but I want to make sure that it doesn't have to be like the perfect I2C master implementation. It just has to be good enough to interact with that piece of hardware. That's really all I care about. But again, that debugging cycle where I'm sitting there for 5 minutes of recompile just to be able to interact with that hardware. So as I'm writing this, I'm interacting with the hardware. That sucks. I mean, now obviously a lot of that can be done in a simulator first, because we can hook that up to Verilator and just like see, okay, yeah, this looks like the good signal. This is roughly what we would expect for an I2C master to send, and then we can put that on the device. And ideally it would just work, but I don't really trust myself to get all that right with just that environment. I want to do it against the actual hardware and test it that way. So what I thought about, though, is that since I2C is not that fast, exactly, Loaded Capo. It's so bad. So what I thought about, though, is I2C is not very fast. And it was actually a picture in this I2C bus specification thing that I found, where this is like I2C.info. Nice little website, by the way. And here it just says, like, here's an example of a network of I2C buses. And obviously the one on my board is not this complicated because it's just the one master is some pins on the FPGA, and then the one slave is that chip, the ADV chip. So it's not this complicated, but I'm looking at this and it said there's a microcontroller here. And here it says I2C port via hardware or bit banging. And that actually got me thinking, because I thought, well, you know, what I can do is I can just expose the clock and data lines as essentially GPIO registers to my CPU. So I can have essentially just low or high, where I map high to high impedance and then low just as low, because they're open collector in I2C. So then I just have these 2 bits of this register that I could write to from my CPU, and then I could also read the values back to get the data. And that would be really easy to make, because it's really easy to hook up that kind of external interface. And then I can just sit there and use my really quick software iteration that I now have because of the ROM loader to be able to get to the point where I'm implementing I2C correctly, at least correctly enough to talk to this chip and actually be able to read and write register values. And when I get that working, then I might just leave it at that. Like, the signal is going to be a little bit messier with the timing and everything, but it should still be perfectly possible to generate a valid I2C signal with that approach, especially because there's no interrupts or anything. So that's the only thing my CPU is actually going to be doing. Obviously, it wastes a lot of CPU cycles, but at the same time, like, the CPU wouldn't be doing anything anyway. And for this kind of design, it doesn't matter. So I think I'm really excited about that, because I think it'll be a really good way to iterate on this, because I can also use the UART on the board to send me feedback. So I could basically just iterate on the code, and that's the only thing I'm really iterating on, and that should be really quick. And then later, if I want to move that into hardware again, then I can pull that up into my simulator again and kind of try to match that with a hardware implementation, which I think was again a really fun way to do that. Yeah, exactly, Dark Saying. That's exactly. You must have typed that right before I said it, because of the stream lag. So totally on the same page. It's exactly it. If I want to put that in hardware later, then I have a nice path to do that. But I think this is by far the easiest and most motivating way to implement that part of this, because once we have that, then we know we can enable the transmitter, and then I just want to put like the simplest hardware we can that can generate a valid signal that will start doing the actual signal generation, and that'll be sort of the first implementation of our GPU, is just some kind of really basic generator, and then being able to turn on this chip. So yeah, I2C isn't that difficult. So it wouldn't be that bad anyway, but I still think it'd be even easier. Why not take the easy route if we have it? So I'll do that first. And then once we can get video output of that, then what I can do is, then I know it works on the hardware. Then I can do one of 2 things. Then I can just start focusing on the GPU stuff directly and start moving forward with that. Or I could implement emulators for just those parts of the hardware that I can put in my simulator setup, which I've also done with like the LED interface, and I also want to do with the UART, which I haven't done yet in my simulator, because then I can do all of the basic hardware implementation, everything, in my simulator flow as well, and I don't even have to touch the hardware once I verify that works. So doing that exploration with the power of the ROM reload and some of the other tooling I made, I think absolutely makes sense. And then the next thing that we want to do, which I would really like to do again in the simulator environment, is actually getting some data from DDR3, because there's essentially 2 halves of the GPU that we need to make. We need to make the part that streams pixels out of DDR at the right timing to get the video out of memory and onto the screen. And then there's the other half, which is going to be the drawing half. And the drawing half, again, is the part that I'm really interested in. But without this other half, it's useless. So that's the part we have to do first. We have to get kind of the whole pipeline working first. And then once we just get this part where the GPU is streaming pixels out of memory, then I can just start doing software rendering as well. So by that time, that's how we're going to start prototyping the actual GPU. So I think that'll be pretty cool. Yeah, and I think that's exactly what these points say underneath. So I think that's the way forward. I want to work on some tooling a bit, in particular this top part. Maybe I do some more of this Python stuff here. Maybe I just put that off because why not? I don't really need. I actually don't mind having half this code in Verilog and half this code in Python. The more I have in Python, the better, because it's easier for me to write and manage. But like I haven't really added any new code in Verilog except some stuff to wire things together, and that I just don't mind. So this workflow is good enough for me, and that's all that really matters. But yeah, I really like this way of moving forward, because then we can get really good iteration time while interacting with real hardware. Which that's one of the things that really sucks with FPGAs, is that it is a long flow to actually get stuff onto the hardware. So if we can avoid that as much as possible, then that's fine. Obviously, it's very exciting when it does run on the hardware, and that's great. In fact, I'm hoping that by the time we start getting the basic GPU working, almost all I'm doing is software work and just kind of playing with it, and I think that'll be really fun. And yeah, obviously it's really exciting to see the hardware actually work on there, so we need to do that periodically, but I don't want to do that for every change that I'm making. So anyway, that was that's all the slides I did. That's all the catching up that I wanted to do, and all the talking, all the stuff I wanted to share with you guys, because that has been the last 2 weeks of my free time. And it's been pretty packed. Been going through a lot of stuff. But I think it's pretty cool. And again, I think looking back on these are the slides from the like kickoff that I did, and we're still pretty in line with this. These constraints are still very important. I want everything to be open source. It still is. Again, I don't have a license, but that's only because I don't know which hardware license to use. So technically, yes, it's unlicensed. So if you don't like unlicensed stuff, I have a good reason, which is that I don't know which license to use. So any help on that would be appreciated. We do have a ridiculous 80s, 90s, 2000s style video game console name, Xenowing, sticking with that. And then again, trying to keep things kind of simple and scoped down. I think we're doing good. Still, this still all fits. Yep. So yeah, I'm pretty pleased. Yeah, there really doesn't seem to be any clear licensing model for open hardware like this. Obviously there's a couple, but they seems to be messy. It seems to be they either grant rights you don't want to grant, or I guess another disclaimer, it's been a long time since I even looked into this, so I'm pulling stuff pretty far out of memory here. And the latency to my mouth is shorter than the latency to this part of my memory, so I might say some things that are just wrong. But I guess the issue is that, like with just software, the software is intellectual property. And so any laws that you have about intellectual property just simply apply to that. And so you could think that is what would work with hardware, but as soon as you put that hardware into silicon, somehow that makes it different. And I don't really understand that. But that means that you actually should use a different kind of licensing for open hardware than you do for open software. I don't understand that, but that's what I'm told. And until I understand that better, I'm not committing to anything, right? So I'm not really sure. I don't really know the best way forward with that. And that's also why every time I bring this up, I ask for advice, because again, I would love to just have this open. Everyone can see it. Everyone can do whatever they want with it. Whether they do or not, I don't care. It's for me. But I want to share it. And yeah. I did look at some other open hardware projects. There were a couple licenses. I don't remember the names of them. There were two that were really that seemed really popular when I looked into this last time, but I don't. It's been so long that I don't remember the details. But yeah, I think you can boil it down to that weird constructor. It's crossing the border between software and hardware patents, and what is intellectual property and what isn't. I don't remember why it was complicated. And maybe there's been a lot of work on that in the last year. I really don't remember. Open hardware license. Yeah, the Taper one and the CERN one. Those were the popular ones, it seemed. Yeah, I just pulled up a random article here because I have to defer to everyone else's knowledge. I really don't understand this stuff that well, so I'm just trying to understand what other people are saying. Yeah, like definitely there's definitely an open hardware movement happening. So this stuff has to come down the line at some point, but I just don't think it's solidified enough yet. Was my impression a year ago. It might be different now. Yeah, like this says, first step is determine if you have anything to license. This apparently knowledgeable person says software is protected by copyright and automatically, so you can safely assume you have something to license when you write software. Open hardware is hardware whose design is made publicly available, so anyone can study, modify, distribute, make, and sell or design hardware based on that design. Yeah, maybe I'm even reading something that's irrelevant here, actually, because this actually seems that it's not describing the problem as I remember it, but I'm not sure. As Creative Commons, also this is a 2011 press release, CERN concurs, saying the covered documentation is limited to schematic diagrams, designs, circuit board layouts, and mechanical drawing. Yeah, this is something I'll have to read on my own later. Really try to digest. I think it would, Grachev, but that makes sense to me. I agree with you, but I don't know 100%. To my knowledge, I think you're right, but I just don't know. And it may be that it isn't important. Like here, I want this code to be open. I don't care. So if I could just like slap an MIT or BSD on it or whatever and just call it good, I'd be thrilled. But it just seemed like enough people were saying it's more complex than that I haven't done that yet. And until I feel like I've had enough people tell me it's okay, I don't want to do any of it. Because there's always that liability aspect. Clearly, I don't think anyone's going to be building missiles with my stupid risc-v implementation. But I would sure hate to get sued if someone did. Now, I really don't think that that's a practical concern, but it'd be nice to do that right. Yeah, exactly. Crowdfund to hire a copyright lawyer. Exactly. Yeah, it would be sad. I thought about how sad that would be, but you're absolutely right. Yeah, my intentions are pretty simple. My intentions are I'm doing this to learn. I'm having a lot of fun. Here's everything I did. Go nuts. I'm not liable. I hope you have fun too. It's annoying to me. I mean, it's annoying to have to license software too. To be honest, like I would love to just have everything in public domain. But I don't know if public domain means you're not covered or means you're okay for like liability cases. I know I'm being pedantic when I bring that up. Like again, it's a practical issue. I don't think any of this would ever come back to hurt me, but like I want to understand that if I'm using a license, I want to understand why and I want to understand how. Maybe I'm just being pedantic. But in any case, we don't really have that much time. This took me a long time to talk through the things I wanted to share, which I'm happy about because I had a lot to share. So maybe we save the actual code for some stuff next week. I was hoping that we could do some of that bit banging stuff, but I could just as well spend like the next sort of week of my time doing most of the other stuff, and then maybe by the time next week rolls around, I haven't done that stuff yet. But I also want to do it this weekend, so we'll see. I also, by the way, I have some time tomorrow night where I was going to work on this stuff, and I might stream for some of that. We'll see. But I think right now it's late enough that I don't want to like dive into this now. Because otherwise I'm going to be up for another 2 or 3 hours, and I can't have that. So I think I'm going to call it quits for today. And then I might stream tomorrow, but I'll definitely be working on this. And then next week, I should be streaming too. Yeah, very busy with the wedding planning. Now, actually, the fiance is handling most of that, which is really nice. So shout outs to her. But yeah, I'm glad you guys had fun. I'm really happy to share this stuff. I'm glad you guys are interested. This is such a fun project for me. So thank you so much. By the way, hedgehogs are really cute. I'm very sorry I forgot to say thank you so much for the bits. Really appreciate that. Lord DeCapo, welcome, by the way. It was fun chatting with you. Glad you liked hanging out with us. And hi to everyone in the stream. Again, sorry about that, but you all know who you are. So Daniel Collins says, if you want something to read after the stream, go to tbl.nu. Yes, also do that. I'm also recommending you do that. Thanks, Mr. Liquid. I need to put the VODs on YouTube. You're absolutely right. We'll do. But yeah, thanks guys for hanging out, and I will see you next time, which is next week, maybe tomorrow. So yeah, see you guys.